In this video, we will explore deadlock detection. If a system doesn't use either a deadlock prevention algorithm or a deadlock avoidance algorithm, then a deadlock may occur. Now the operating system may provide a deadlock detection algorithm to determine if a deadlock exists, or if the deadlock exists, the operating system needs to provide an algorithm to recover from the deadlock. And now we will take a look at the deadlock detection. Specifically, if each resource type has only one resource instance. So that means each resource type has a single resource instance. In this case, we can detect deadlock using wait-for graph. Wait-for graph is a variant of resource allocation graph. To convert a resource allocation graph to a wait-for graph, we need to remove the resource nodes or the resource vertices. We only keep the thread nodes. And we also need to collapse edges. Assuming we have a request edge, the thread TI request resource RI, and the resource RI is allocated to thread TJ. Now we remove this resource node. We add an edge between the thread TI and TJ. So we get this edge from TI to TJ. This means thread TI is waiting for TJ to release a resource. In the wait-for graph, so we can use a wait-for graph to detect deadlock. A deadlock exists if and only if wait-for graph contains a cycle. If there is a cycle, this means there is a deadlock. If there is a deadlock, so we can see a cycle in this graph. Operating system need to maintain wait-for graph and periodically evoke the cycle detection algorithm. The cycle detection algorithm, the time complexity of the cycle detection algorithm is big O n squared. N is the number of threads or the number of vertices in the graph. Now let's take a look at an example. On the left side, this is a resource allocation graph. We have thread nodes and we have this resource node. Now we will convert this to a wait-for graph. We start from the T1. Now T1 requests R1. And R1, this resource is allocated to T2. And we remove the R1 node. We add an edge from T1 to T2. So this means that T1 is waiting for T2 to release a resource. And the T2 requests R3. R3 is allocated to T5. So we remove the R3 at an edge from T2 to T5. And then T2 requests R4, and R4 is allocated to T3. So we remove the R3, no, we remove the R4, we add an edge from T2 to T3. Now T3 requests R5. R5 is allocated to T4. So we remove R5 and add an edge from T3 to T4. And T2 requests R5. R5 is allocated to T4. So we add an edge from the T2 to T4. Last one, the T4 requests R2. R2 is allocated to T1. So we remove this R2 and we add an edge from T4 to T1. Okay. On the right side, this is the corresponding waitful graph. In this graph, we have a cycle here. T1 wait for T2, T2 wait for T4, and T4 wait for T1. This is a cycle. Okay. T5 may get the resource and can terminate, and T5 can release the resource. T2 get this resource, but T2 still needs the resource, still waiting for the T3, and T3 waiting for the T4. T4 is waiting for the T1. So here we have two cycles. So there's a deadlock in this, there's a deadlocks here. Okay. In next video, we will talk about the deadlock detection when each resource type has several resource instances. We will talk about in the separate video.